In this video, we're going to look at a labor and capital model, so from economics, and how Lagrange multipliers can tie into this kind of model. We're going to look at a production scenario where we produce Q units of a product, and what influences the amount that we can produce is the number of workers, W, and the units of capital investment, K. And we have a nice relationship here between these two elements, and the idea, and typically, would be to maximize the quantity that we can produce. So this would be the function that we want to optimize, and just note that it's no longer a function of x and y, it's a function of w and k. Just looking at this function initially, it makes sense that we would try to maximize our production by increasing the number of workers and increasing our capital, because increasing both of those will increase our production. However, that doesn't necessarily work with the real-world constraints. In particular here, we've been told that we can only spend $3,200. And we can divide that spending between our workers and our capital. So this is going to be our constraint. Now, how can we divide that $3,200? We're told that each worker unit here costs $10 and capital units are $20 each. And so our budget then becomes our constraint, which is whatever we spend has to add up to $3,200. And if we choose to hire X workers or W workers, each one of them is going to cost 10. And whatever units of capital we intend to produce, each of those is going to cost $20. So this will become our constraint function. And that matches perfectly with what we've seen before, only now it's a function of W and K. And this is a lowercase k, let's call it C, to make it separate from our usual constraint construction. So there's a function that has to equal some certain amount. We can only choose W and K values that satisfy that. With that constraint, we want to maximize the quantity produced. With that in mind, we can then try to set up our Lagrange multiplier equations. So our starting point is our two partial derivatives with respect to W and K this time. And our function is up here, and we're taking the W derivative, so being careful with our constants. The 6 is a multiplier, it stays. W is our variable. We bring the 3/4 in front, and we subtract 1 from the power, gives us W to the -1/4. And K is a constant for that derivative, so we get 1/4 power staying around. We then do the same calculation with the K as our variable. So 6 and W to the 3/4 are constants. K to the 1/4, when we differentiate, we get 1/4 K to the 1 less, which is -3/4 as the exponent. We then set those equal to lambda times the G derivative. The derivative of G with respect to W is just 10, and the G derivative with respect to K is 20. This is our GW derivative, and this is our GK derivative. These become our usual equations 1 and 2, and our constraint itself is our equation 3. We have to satisfy our budget, but if we're looking for optimal production, we have to have the gradient of our production function match the gradient of our constraint function. We now dive in and we try to solve those equations. We'll copy these to the next page. Starting with those equations rewritten, a very useful strategy when we're focusing our attention on the W and K and that we don't care so much about the lambda values is to take our two equations, 1 and 2, and simply divide through 1 divided by 2. When we do that, we simply take the left-hand side of this equation and divide it by the left-hand side of this. That gets what it gets. But you can see when we divide the right-hand side of this by the right-hand side of this, the lambda values will cancel. It turns out to be a very efficient way to get rid of the lambdas and then back into focusing on the W's and the K's. We'll do it explicitly here so we can see all the details. We have 6 times 3/4, W to the -1/4, K to the 1/4, all over 6 to the W to the 3/4, 1/4 multiplier K to the -3/4. That is equal to 10 lambda over 20 lambda. And there's now a ton of cancellation that we can do. The lambdas go away, the 10 and the 20 actually become 10 and 2, the 6 cancels, the quarter and the quarters go away, and then we can start doing a little bit of tidying here. The right hand side is a half, we have a 3 over 1, so that's just a 3, and then w to the negative 1/4 divided by w to the 3/4, we subtract powers when we divide. That's going to give us w to the negative 1. And the k's, interestingly enough, work the other way. We have positive 1/4 minus 3/4. That's 1/4 plus 3/4. We get k to the positive 1. And then we get an equation that's a lot easier to work with. In fact, we can actually solve for k. It's going to be 1 over 6 times w. Because w to the negative 1 is like 1 over w. We bring it up to the other side, and we get a nice simple relationship between the units of capital and the units of workers at the optimum value. We can now combine that with our budget constraint. So we grab our budget, bring it over to the other page, and see where that gets us. We now know that our capital is going to be 1/6 times the number of workers. Plugging that in gives us 10 W's plus 20 over 6 W's, W over 6, equals 3,200. We can multiply through by 6 to get 60 workers plus 20 workers. This times 6 is 19,200. And so W is equal to, there's 80 of those, 19,200 over 80. And we get 240. So the optimal number of units of workers that we want is going to be 240. And from there, we can combine these two equations and find our K optimal is going to be 1/6 of 240, and that is 40. So this is telling us we should invest, or we should spend our budget in such a way to invest in 40 units of capital and 240 workers. And that'll produce the optimum quantity of production for this particular scenario. And we can actually calculate that quantity that will actually end up producing 6 times our W value, 240 to the 3/4, times 40 to the power of 1/4, 920 units. And so that would naturally be the completion of a Lagrange multiplier problem. What we're going to see in a subsequent video is what can we interpret or add to this if we knew what the lambda value was, and what kind of information would that tell us about some hypothetical changes to our budget. We'll see that in an upcoming video.